Look up on a clear night, maybe with a small telescope, and you might spot these faint, often beautiful patches of light. Sometimes they look deceptively simple, like little fuzzy planets.
Mm.
But peer closer, or just know their story, and you realize they are among the most dramatic objects in the universe. They are planetary nebulae.
And they are anything but planets.
Right.
In fact, they represent a star's, well, its grand finale.
Right. And here on the deep dive, our mission is simple. Take a pile of research, articles, and notes, and dig out the absolute most fascinating, must-know insights for you, the listener.
Yep.
Today, we're taking a deep dive into these cosmic gems, and specifically how one space mission, the European Space Agency's Gaia spacecraft, is fundamentally changing everything we thought we knew about them.
It really is a revolution in this field. We're going to unpack what these incredible objects actually are, grapple with the huge challenges astronomers faced in studying them for centuries, and discover how Gaia's unprecedented precision is now revolutionizing our understanding.
Understanding their distances, right,
Right.
and their journeys through the galaxy.
Exactly. Their distances, their motions, those intricate shapes they have, and even the sort of secret lives of the stars at their hearts.
Our dive today is centered around a really insightful text that lays out exactly how Gaia has contributed to this specific, vital area of astronomy. So, let's get into it. What are these things, really?
Okay, let's unpack this. First off, just like the name Planetary Nebulae, which is, well, it's a fantastic historical misnomer from William Herschel.
Right, he just thought they looked around like planets.
Yeah, through his telescope back in the day. But they have absolutely nothing to do with planets themselves forming. Zero.
Got it. So that's just old terminology sticking around. What's the reality then?
The reality is far more dramatic. We're talking about stars like our sun, but much, much older, nearing the very end of their lives.
Okay.
Specifically, stars with masses between about 1 and, say, 8 times the mass of the sun when they enter a phase called the asymptotic giant branch, or AGB.
AGB. This is after they fused all the hydrogen in their core, right? They swell up into red giants.
Exactly. The core contracts, heats up like crazy, while the outer layers expand dramatically and cool way down. Eventually, that contracting core gets incredibly hot, around 100 million Kelvin.
Wow.
And that's hard enough to start fusing helium. So you end up with this dense core of carbon and oxygen, surrounded by active shells where helium and hydrogen are still burning.
Okay, here's where it gets really interesting and kind of violent, isn't it?
It absolutely is. That helium fusion process, it's incredibly sensitive to temperature, super unstable.
Unstable, how?
It leads to a series of violent pulses. The star basically starts, well, convulsing, experiencing these thermal pulses that cause it to eject huge portions of its outer atmosphere in successive waves.
So it's literally shedding its skin layer by layer, puffing it off.
Precisely. And as it sheds those outer layers, hotter and hotter material from the star's core gets exposed.
Right.
When that remaining core gets hot enough, reaching temperatures around, say, 30,000 Kelvin, its intense blast of ultraviolet radiation hits the gas that was just ejected.
And that's what makes it glow, finally.
Yes, exactly. That UV radiation ionizes the gas, strips electrons from the atoms, and as those electrons recombine with the atoms, they emit light, brilliant light.
Often in those stunning colors we see in photos.
Right, depending on the elements present, like oxygen gives you that greenish color. Hydrogen is often reddish.
So they're not cosmic nurseries where stars are born. They're literally the colorful, glowing ghost of a dying star like our sun.
That's a perfect way to put it.
Yeah.
And because they represent this crucial final phase, they are invaluable to astronomers. Absolutely key probes.
Probes for understanding how stars live and die.
Stellar evolution, exactly. And they play a vital role in cosmic chemical enrichment. Think about it. They are returning elements forged inside the star, heavier stuff like carbon and oxygen, back into the interstellar medium.
Material for the next generation of stars and planets.
That's the cycle. It's a huge cosmic legacy.
And the first one ever spotted was the Dumbbell Nebula, M27, back in 1764.
Correct. By Messier. We know of about 2,000 in our galaxy today, roughly. But the estimate for the total number lurking out there is closer to 20,000.
20,000, so we've only seen the tip of the iceberg.
Pretty much. And for the longest time, figuring them out was incredibly frustrating because of one major problem: distance.
Knowing how far away they are, that sounds fundamental, doesn't it?
Absolutely fundamental. If you don't know the distance, you can't know the true size, the true luminosity, its brightness, or even its true motion through space. Nothing makes sense without the distance.
And they're far away.
Typically hundreds of parsecs away, often much, much more. A parsec, just for reference, is about 3.26 light years. So, vast distances.
And that's too far for parallax from the ground.
Generally, yes. Parallax is that tiny apparent shift in a star's position as Earth orbits the sun. It's the most direct way to measure distance. But for most PN, that shift is just too minuscule for ground-based telescopes to measure accurately. The atmosphere gets in the way, limits the precision.
So if direct measurement was off the table for most, how did scientists even try to estimate distances before space missions like Gaia?
They had to get creative. They relied on indirect methods, which were often based on assumptions. Assumptions that, well, turned out to be flawed sometimes.
Like what kind of assumptions?
Think of it like trying to guess the size of a balloon across a field. If you assume all balloons are the same size, you can use how big it looks to guess its distance.
But what if the balloons are actually different sizes?
Exactly. Your guess is wrong. So previous methods used everything from how bright the nebula appeared overall, its surface brightness, to analyzing specific absorption lines in the light, like interstellar sodium lines, or using complex spectroscopic models.
Or just assume it?
Or just assuming, yeah, that all PN had roughly the same physical radius or the same amount of ionized gas. Lots of assumptions.
You're saying those assumptions weren't great, led them astray?
The impact of this difficulty was immense. Before Gaia, honestly, only a tiny, tiny fraction had distances known with anything you'd call reasonable accuracy.
How tiny?
Well, one estimate from 2008 suggested maybe fewer than 50.
50.
Out of around 1,800 known nebulae back then,
Huh.
had good distance measurements.
Wow, that's almost nothing.
It was a massive bottleneck, preventing real progress in understanding them. You mentioned the Hubble Space Telescope earlier.
Yes, I read that HST offered some help before Gaia. How did that work?
It did provide a bit of a lifeline. By observing PN in the large Magellanic Cloud that's a nearby satellite galaxy,
Right.
these PN were so far away they just looked like points of light, unresolved. But HST could measure their apparent angular sizes with higher precision than ground telescopes. This gave one of the better indirect ways to estimate distances to similar objects in our own galaxy, sort of a calibration point, before Gaia came along.
Okay, so we had this massive problem, a huge bottleneck in understanding, relying on shaky assumptions. Then came Gaia. How did this mission fundamentally change the game?
Gaia is a game changer because it's specifically designed to do one thing exceptionally well: map the positions, distances, and motions of billions of stars across our galaxy with absolutely unprecedented accuracy.
Billions, including the central stars of these nebulae.
Yes, including those crucial central stars. For planetary nebulae, this is the first time we could get precise parallax measurements, those direct distance measurements, for a huge number of these objects. Hundreds.
And not just get the distances, but also check the old methods.
Yes. Perhaps most critically, it allowed astronomers to finally test how accurate all those older, indirect, assumption-based methods really were, but put them head-to-head with solid data.
Okay, so the results start coming in. Gaia Data Release 2, DR2. What did that reveal when they compared Gaia's numbers to the old guesses?
This is where the revolution really began. Studies using Gaia DR2 data identified hundreds of the central stars of known PNA. Now, when they compared Gaia's super-accurate parallaxes to the few previous accurate measurements we had, say from the USNO parallax program or some HST work,
They matched up.
they matched up beautifully. That gave everyone confidence in the Gaia results.
Okay, good. But the older, assumption-based methods, the statistical ones, the spectroscopic ones.
Here's the shocker. Distances estimated using those older statistical or spectroscopic models were often found to be significantly overestimated, sometimes wildly overestimated.
Overestimated, so the nebulae were actually closer.
Many of them, yes, significantly closer than we previously thought based on those older methods.
Wow, that's a massive recalibration. It must have changed everything about how we view these objects, their place in the galaxy, their actual sizes.
It absolutely did. Getting distances right is fundamental. It changes everything downstream. DR2 data also immediately allowed scientists to calculate the true physical sizes of the nebulae, because now you know the distance and you can measure the angular size.
Right, simple geometry, though.
Exactly. And they could also estimate their kinematical ages.
Kinematical age. What's that again?
It's basically an estimate of how long ago the gas was ejected. You calculate it by dividing the physical radius of the nebula, which we now know thanks to Gaia's distance, by its measured expansion velocity, which we can get from spectroscopy.
Okay, so size divided by speed gives you time. Makes sense.
Right. And what they found was a clear link between this kinematical age, or size, and the evolutionary stage of the central star.
How so?
Nebulae, with smaller physical radii, were typically associated with younger central stars, still shining brightly, kind of in a constant luminosity phase, while the larger nebulae generally came from older central stars that were starting to fade as they head towards becoming white
So
dwarfs.
you could see the evolution laid out spatially.
In a statistical sense, yes.
Yeah.
And with better distances for hundreds of them, you could finally get a much better handle on the total population of the galaxy.
Did the estimate change much? That 20,000 number?
Using the DR2 distances, researchers came up with an estimate around 21,000 planetary nebulae in our galaxy. So it confirmed the rough scale of previous estimates, but now is based on solid distance data for a large sample,
Much more reliable.
much more. And they could also map their spatial distribution, where they actually are in 3D space, determine things like their scale height, their average height above or below the main plane of the galaxy,
Which was?
around 168 parsecs, give or take, and their space density, how many are packed into a given volume of space, about 64 per cubic kiloparsec. Real numbers, finally.
And Gaia kept delivering data, right? What about EDR3, the early data release 3? Did that refine things further?
It absolutely did. EDR3 built on DR2 with even more central stars identified and even higher precision measurements for parallax and motion. Catalogs suddenly became available with over 1,700 PNE having reliable Gaia distances.
1,700, that's a huge jump from maybe 50 before Gaia.
Massive jump. This refined our understanding of their distribution, their sizes, their evolutionary states even further. And the accurate distances were so good, they even allowed researchers to propose a new, more reliable distance scale for PN based on the relationship between their radius surface brightness and their physical radius, all calibrated using Gaia distances.
So Gaia basically provided the anchor, the ground truth for distances.
Precisely.
Okay, so Gaia gave us distances, completely recalibrating our view. But the sources also talk about how it's revealing their journeys through the galaxy. It's not just about where they are, but where they're going.
Yes. This is another fascinating layer. Gaia measures not just distance through parallax, but also the proper motion of stars. That's their apparent movement across the plane of the sky over time.
Like how fast they're drifting sideways.
Exactly. Combine that proper motion with the distance, and you can calculate their velocity perpendicular to our line of sight. And if you add in the radial velocity from spectroscopy, how fast they're moving towards or away from us, you get their full 3D space velocity.
The complete picture of their movement.
The complete picture. And the motion of that central star is incredibly revealing about the nebula itself and its history.
Can you give an example? How does the star's motion affect things?
Absolutely. Take the planetary nebula known as SG-268. It has this strange long tail extending from it.
Ah, tail.
Yeah. And Gaia data shows the central star is moving really rapidly through space. That tail is almost certainly material being stripped off the main nebula shell as the star plows through the denser interstellar gas of the galaxy.
Wow. So the star's speed is literally dragging gas behind it, shaping the nebula in real time.
It seems so. Its motion is actively interacting with its environment and shaping the nebula we see. It's not just passively expanding.
That's incredible.
It is. And these motions also help us understand where these stars originally formed and which part of the galaxy they belong to. We can classify them into different galactic populations, like the thin disk, which is where the sun lives, younger stars, or the older, thicker disk, or even the halo,
Based on how they're moving.
based on their velocity and direction. For example, the motion of the central star of another nebula, SJ2174, it's an extreme velocity case, probably originating from the thick disk population. Its high speed also explains something puzzling,
What's that?
why the central star is now noticeably offset, quite far displaced from the geometrical center of the nebula shell. It's simply moved that far over the thousands of years since the gas was ejected.
The star just kept going while the shell expanded more slowly.
Exactly. The kinematics tell the story.
Speaking of shapes, we touched on how they're not simple spheres. The sources really highlight that most are incredibly complex, visually stunning.
Oh, they are. Visually, they're some of the most beautiful objects out there, and incredibly diverse. You see everything from relatively simple rings and bubbles to highly elongated shapes, dramatic bipolar structures that look like hourglasses.
Like butterfly wings sometimes.
Exactly. And even intricate jets of material blasting out from the center. They're rarely just perfect spheres.
And what's thought to be causing all this amazing variety in shapes? It can't just be the star puffing off gas evenly.
No, definitely not. It's still an active area of research, a big puzzle. But the primary suspects are things like having a binary central star.
Two stars orbiting each other.
Yes, the gravitational interaction between two stars can really focus the outflow, maybe create a disk around them that channels the ejected material into bipolar shapes.
Okay, so binaries are important. What else?
Complex stellar winds interacting with each other or with previously ejected material, and magnetic fields, the star's own magnetic field or fields generated in that binary interaction, could play a big role in channeling the gas.
Magnetic fields shaping cosmic sculptures.
Essentially, yes. And I read that they're even investigating if planets orbiting the star could play a role. That seems wild.
It does, but it's a serious hypothesis.
Yeah.
The idea is that substellar companions, so things like large gas giant planets or maybe brown dwarfs, orbiting close to the central star could also influence the outflow. Maybe they get engulfed during the giant phase, or their gravity helps shape the ejection process.
So the star's own planetary system could influence its death shroud.
It's possible. This complexity, the morphology, is a key area where better data, like distances and understanding the central systems, is helping us piece together the underlying physics.
And that brings us perfectly to another really exciting area where Gaia is making huge inroads. Finding those hidden companions you mentioned, binary, or even triple star systems at the heart of these nebulae.
Yes, this is becoming increasingly clear. Many, perhaps even most, of the stars creating these beautiful nebulae are not single stars like our sun might be. We now know of about 50 central stars confirmed to be in binary systems, and at least 2 that are in triple systems.
Triple systems. Yes. And Gaia data was actually crucial in confirming one of those triples, called SP3, with its precise parallax and proper motion showing 3 stars moving together.
Why are these binary and multiple systems considered so important in this context? What difference does it make?
Well, there are strong suggestions, as we mentioned, that being in a close binary system might be crucial for creating the most complex and dramatic shapes driving those jets, or collimated outflows, or those low ionization structures you sometimes see.
So the companion star is an active participant in shaping the nebula.
Very likely, especially if they're close. There's even speculation that interactions in a binary system could affect the nuclear fusion processes happening inside the star late in its life, the nucleosynthesis. That's still debated, but it's an intriguing possibility.
Okay, so finding these companions is key. How is Gaia helping astronomers actually find them, especially if the companion is faint or far away?
Gaia offers a couple of powerful ways. For wider binary systems, where the companion star is relatively far from the central star.
Like orbiting way out.
Right. Researchers are using Gaia's amazing precision in parallax and proper motion. They basically search the Gaia catalog for any other stars located near the known central star on the sky that have the exact same parallax, meaning same distance, and the exact same proper motion, meaning moving through space together.
Like finding fellow travelers moving in lockstep?
Exactly. It's called searching for common proper motion pairs. And studies using DR2 data were very successful with this. They confirmed that NGC 246, for instance, is indeed a triple system. And they found wide companions orbiting some central stars surprisingly far out, up to 15,000 astronomical units.
And 15,000 AU is, let's remind us, that's roughly 15,000 times the distance from the Earth to the Sun, correct? That's huge.
Exactly. A vast distance, but apparently still gravitationally bound in these cases. However, interestingly, the studies looking at these wide binaries haven't yet found a clear, strong correlation between having a wide companion and the nebula having a complex, non-spherical shape.
So maybe the wide companions don't influence the shaping as much. It's the close ones.
That seems to be the leading idea, yes. The action happens when they're close together.
Okay, but what about those close binaries? Where the stars are much nearer each other, those must be much harder to spot visually, or even by just looking for shared motion if they're unresolved.
Much, much harder. They often look like a single star. But scientists are using a really clever technique with Gaia's photometric data. It's brightness measurements.
How does that work?
Gaia takes many, many repeated measurements of a star's brightness over its multi-year mission. If that brightness varies significantly over time, and especially if it varies in a complex, non-periodic way, that variability gets captured in the statistical uncertainty of the average brightness measurement reported in the Gaia catalog.
So a high uncertainty in brightness means the star isn't constant.
Exactly. It can be a strong indicator of a close binary system. Maybe one star is eclipsing the other. Maybe there's an accretion disk flickering. Maybe ellipsoidal variations due to the stars distorting each other. All sorts of things can cause variability in close binaries.
That's fascinating, using the measurement uncertainty itself as a clue to hidden companions. Has this method actually worked?
Yes, it's proving quite powerful. Using Gaia's photometric data and the associated uncertainties from DR2 and now EDR3, researchers have successfully recovered many of the previously known close binary candidates among central stars.
That builds confidence.
Right. And excitingly, they've also flagged a number of new potential close binary systems that weren't suspected before, which now need follow-up spectroscopic observations to confirm.
So more discoveries are likely on the way.
Definitely. Though, as a quick note, this variability method isn't perfect. Some previous candidates identified this way have turned out, on closer inspection, to be a different type of interacting binary called symbiotic stars, which involve a white dwarf accreting from a red giant companion. They're related to PNA evolution but are a distinct class.
Okay, good clarification. So Gaia is mapping the main population in the galactic disk, revealing binaries. But the sources also mentioned finding these objects in different, perhaps more exotic galactic neighborhoods too.
Yes, that's right. Planetary nebulae aren't confined just to the main disk and bulge of the galaxy. We find them in older, different stellar environments too, like galactic globular clusters.
Those incredibly dense, ancient, spherical collections of stars orbiting the galaxy?
Exactly. Very old populations. 4 PN are currently known within globular clusters in our own Milky Way.
Only 4. They must be rare there.
Relatively rare, yes, given the age and stellar types in globular clusters. And they're even found in some small nearby dwarf galaxies that orbit the Milky Way, like the Fornax dwarf spheroidal galaxy, where 2 are known.
And what's their value when found in these other environments? Why is it interesting?
They are incredibly valuable in those contexts. In globular clusters and nearby galaxies, they can act as important standard candles, or maybe standardizable candles, to help measure the distance to those systems.
How does that work?
There's a technique called the Planetary Nebula Luminosity Function, or PNLF. The idea is that the very brightest planetary nebulae in different galaxies seem to have a similar, consistent maximum true luminosity. So by measuring how bright the brightest ones appear in a distant cluster or galaxy, you can estimate the distance to that entire system.
Oh, another way to gauge cosmic distances.
Yes, and Gaia data is key here too, even for these external systems. It helps confirm whether these PNE candidates are truly members of the clusters or dwarf galaxies they appear in.
How?
By checking if their proper motion, measured by Gaia, matches the overall average motion of the stars in that cluster or galaxy. Gaia DR2 data, for instance, was used to confirm the membership of PS1, the globular cluster M15, and GJJC1 in M22, based on their motions matching the clusters.
So Gaia helps verify they actually belong there before you use them to measure distance.
Exactly. Got to make sure they're actual residents, not just foreground stars that happen to lie along the same line of sight.
Okay, so beyond these big statistical surveys and population studies, does Gaia's data also allow for sort of deep dives into individual specific planetary nebulae, focusing on one object story?
Absolutely. That's another major impact. The precise distances and motions from Gaia allow astronomers to pick out individual interesting objects and really zoom in, investigate their specific history and physics in much greater detail than was possible before.
Can you give some examples mentioned in the research?
Sure. The source material highlights several cool examples. Using Gaia data to investigate the origin of a very faint extended ionized halo around a nebula called IC 5148. Or using Gaia's motion data to show decisively that a particular central star thought to be in the star cluster, NGC 2452, is actually not a member. It just happens to be passing through. Same for NGC 2453.
So debunking assumed connections.
Right. Or conducting really detailed studies of the central star system of NGC 2346, which is a known binary. And another neat one, confirming that a specific bipolar nebula and its central white dwarf star are indeed true physical members of the open star cluster M37, which helps constrain its age and evolution.
It sounds like before Gaia, with all the huge uncertainty about how far away these objects really were and how they were actually moving through space, astronomers were fundamentally limited. They couldn't really push their models too hard, could they?
That's exactly the heart of the issue. The enormous uncertainties, especially in distance, were the biggest hurdle. It's like trying to build a precise model of a complex machine when you don't know the exact size or speed of the most crucial parts. Your model can only be so good.
Limited by the input data.
Precisely. But Gaia's incredibly precise measurements are finally providing that fundamental reliable data, the distances, the motions. This allows for much more rigorous quantitative testing of the complex physical models that describe this brief, vital, and pretty spectacular phase of stellar life. We can really start to hold the theory's feet to the fire, so to speak.
So, what does this all add up to then? Taking a step back, it feels like Gaia hasn't just given us better numbers, better distances. It's fundamentally rewritten a chapter in stellar astronomy, hasn't it?
It truly is a transformation for this field. You could say Gaia has provided the missing bedrock. Its data has allowed us to map the location and movement of planetary nebulae across the galaxy with unprecedented accuracy.
A true 3D map with motion.
Yes. And this new foundation of data is allowing us to test, refine, and sometimes completely overturn our previous models of how stars eject their atmospheres, how these beautiful glowing shells form and evolve, how the central stars themselves behave, and where they fit into the grand tapestry of the galaxy's history and structure.
And it's really highlighting just how diverse these objects are, isn't it? Shaped by this complex interplay of internal stellar processes, those powerful stellar winds, maybe magnetic fields, and perhaps most intriguingly, the dynamic influence of binary companion stars or maybe even unseen planets.
Absolutely. What's fascinating here is that this relatively short period in a star's life, a planetary nebula phase, might only last for, say, a few tens of thousands of years, which is an eye blink in cosmic terms.
Right, very fleeting.
Very fleeting. But it's incredibly information rich. It encodes so much about the star's final evolution and its environment. Gaia is giving us the key to start decoding that information much more effectively.
So, as Gaia continues its mission, potentially releasing even more precise data in future releases, considering the incredibly complex way these nebulas form, this whole ejection process, the sheer variety of shapes possibly influenced by hidden companions like other stars or even giant planets, and the dynamic paths these dying stars trace as they move through the galaxy. What other fundamental surprises do you think are still locked away in this dazzling, brief final act of a star's life? What might we learn next?